In this video, I will sketch for you a way to do a general analysis of the two-terminal MOS structure. We will develop equations that will be valid for any surface condition, be it accumulation, depletion, or inversion. Here is the structure we have been discussing, the general MOS structure with the general voltage VGB. The surface potential between surface and bulk is Cs, the oxide potential is Psiox, and at any point y, the potential between that point and the bulk is Psi of y. We need to write equations for this structure that can predict what will happen for any value of VGB, whether it is in depletion or at flat band or in inversion or in accumulation. We have to start like this, and once we have the general expressions, then we will simplify it for particular regions, notably the regions of inversion that we are mostly interested in. So we start with this equation, which we have already used. This relates the ratio of electron concentration at a point y to the bulk, so n of y to n 0. And we have the exponential that involves the potential from the point we're interested in to the bulk, Psi of y, divided by the thermal voltage. We already know that there is a corresponding equation for holes, which is the same form, except it has a minus sign here. And we also know that the total density at any point y, in general, can consist of holes and electrons and ionized acceptor atoms and ionized donor atoms with these signs. We covered this in our background review. Finally, we have related charge density to potential by using Poisson's equation, which is shown here. Second derivative of the potential with respect to position, rho is the total density over here, epsilon sub s is the permittivity. Now, if you manipulate these equations, you can derive the following result. I'm going to bypass a lot of mathematical steps. If you are interested, you can find them in Appendix C of the book. So starting from these equations, we get this result. It looks kind of very long, but in fact, it is written in a form that is probably clearer than any form you may have seen in semiconductor books. The reason is that if you trace the development of this equation, you can clearly identify where each term comes from. This one comes from the hole contribution, if you have any holes in the surface, for example, in accumulation. This comes from ionized acceptor atoms, and we even allow for the presence of donor atoms at the same time. I forgot to say that this is possible in general because sometimes you may have an N-type region, and to convert it into a P-type region, you diffuse enough acceptor atoms so that the overall population of acceptors is larger than that of donors, and the difference is the effective acceptor concentration. So to allow for such a general situation, I have allowed both for N sub A and N sub B, N sub D here. And finally, this term is due to electrons. This is the contribution of electrons to the whole charge. So now we have an equation that gives you the total charge QC per unit area. That's what the prime sign means here, as a function of the surface potential. This term here, sine of Cs, is simply 1 if Cs is positive, it is 0 if Cs is 0, and it is equal to minus 1 if Cs is negative. If you work with this equation, and you make certain assumptions and substitutions, again I have to skip the steps, but they are in the book, you find this equation, which is closer to the equation you see in semiconductor device books. So here is a repeat of this equation. It relates the total charge in the semiconductor to Cs, where Cs is the surface potential. We also know that the gate charge is the oxide capacitance times the oxide potential. This is the same as what you would have in a linear capacitor. We also know that the sum of the gate charge, effective interface charge, and space charge is 0. Finally, we have the potential balance equation, which we have shown before, and it is this one. Now, if you look at this set of equations, what do you see? You see 4 equations in 4 unknowns. VGB is applied externally, so this is supposed to be a known voltage. The only unknowns are 2 charges, gate charge and semiconductor charge, and 2 potentials, the oxide potential and the surface potential. Now, in principle, having 4 equations with 4 unknowns, you should be able to solve them. Unfortunately, because of this equation, it's not possible to really have explicit solutions, so you must resort to numerical solutions for this. Nevertheless, we can do something useful here. We're going to eliminate some unknowns between these equations and end up with this equation. What is this equation? This equation relates the surface potential PS, which appears at various places here, to the externally applied voltage. So in principle now, we have finally a result that allows us to calculate the surface potential as a function of the externally applied voltage. If we know the surface potential, then we can find the inversely layer charge and we can end up with the MOS transistor equations. That is why we're doing all this. This is probably the longest equation we'll ever see in this book, and pretty soon I'm going to simplify it further. This quantity here, the square root divided by Cox prime, will be called gamma. This will turn out to be the body effect coefficient that you may have actually already used in simple models for MOS transistors. We'll come back to that. So we can solve this for CS for a given VGB to find the surface potential. And then once we have the surface potential, we can plug it into this equation at the top and find the space charge. So we can plot these things. In fact, to plot this one, it turns out you don't even have to solve this numerically, because what you can do is you can give values to CS, calculate the right-hand side, and find VGB. So now you can create CS, VGB points and plot them. So let's see what these plots look like. This is what I just mentioned, the plot of CS versus VGB, and I subtracted the flat band voltage here to make things cleaner. This is the total semiconductor charge as a function of the same quantity, VGB minus the flat band voltage. So let's interpret these plots, having in mind this general structure. So let's start with the charge. It says that if VGB minus VAB is negative, in other words, VGB is less than VFB, we are in accumulation and the charge is positive. It should be, because over here we would get holes in accumulation, as we have already discussed. Then if VGB starts becoming larger than VFB, so when this is positive, we have depletion. The charge becomes negative and increases because we are depleting acceptor atoms. And finally, when this is large enough, you start getting electrons at the surface, and now the charge becomes significantly more negative because of the presence of electrons. Let's look at this plot. When VGB minus VFB is negative, we are in accumulation, and the surface potential is negative, as we have already mentioned. When we are in depletion, the surface potential is positive, and it depletes the semiconductor. You have ionized acceptor atoms, and as you increase VGB, you deplete more and more, and the surface potential goes up. And finally, the surface potential flattens out like this. Why does this happen? It happens because at such values of VGB, the surface potential is so large over here that the surface starts becoming very attractive for electrons. You may recall that the concentration of electrons at the surface is exponentially related to the surface potential. So once that exponential takes off, then you can have plenty of extra charges here without having to increase CS very much. So as VGB becomes large, the charge in the semiconductor, which will start being mostly due to electrons, can become large without having to increase the surface potential very much. Now, here, this region is called inversion. We can define it more precisely later on. The beginning of this region is weak inversion. Then we get into moderate inversion, and when this flattens out, we are in strong inversion. We will come back and define these things more precisely later on. Now we can simplify these results in particular regions. Let's, for example, assume that we are deep in depletion where psi(s) is positive, and deep in depletion means we have a psi(s) larger than several phi(t), but not as high as phi f. So now certain terms become completely negligible. And we also know the sign over here. The sign of psi(s) is positive because we are in depletion. Therefore, the function sign of psi(s) is equal to +1. This term is completely negligible because it is an exponential to the negative quantity, and the absolute value of the quantity is large. So this we can neglect. The same thing happens here. This is an extremely small quantity multiplying this whole thing, so you can forget about all this. And even phi(t) can be neglected compared to psi(s). So sometimes we like to leave phi(t) there, but it really does not make much difference for our purposes, so I will be neglecting it. You can do the same with the equation we had for VGB versus psi(s), and we get the corresponding equation like this. So now we have simple results for deep in depletion. Let me summarize the results. These equations, after you eliminate these extremely small terms, become like this. This is the charge, and this is the gate body voltage. Notice now we have very simple expressions. The charge in the semiconductor in depletion, which is due to ionized acceptor atoms, is proportional to the square root of the surface potential. And VGB is related to psi(s) in this way. Remember that in the general equation we had that related VGB to psi(s), we could not solve explicitly for psi(s). But this one, of course, we can solve explicitly for psi(s), and the result is this. So this now gives you the surface potential for a given VGB explicitly. This expression, which is the surface potential in depletion, will be called psi(sa), and we will have use for it pretty soon. Here is a plot of psi(s) versus VGB minus the flat band voltage. As we've seen in the previous slide, it flattens out like this in strong inversion. And psi(sa) is this expression, and it goes like that. You can see now that in depletion, the two are extremely accurate. They practically coincide, but not only do they coincide in depletion, they even coincide in the beginning of the inversion region, which is the weak inversion region. So in fact, what we will be doing later on is we will approximate the surface potential in weak inversion by psi(sa). So we have seen a way to analyze the semiconductor in a very general way, resulting in equations that are valid in accumulation, depletion, and inversion. In the next video, we will focus on the most important region for us, inversion.